are focused on providing better methods to assess resources across large spatial and temporal domains. Kevin.
Thank you. What I'm going to present this morning is really a function of thoughts that I've had over the last several years, an evolution, if you will, of thinking about this issue of how we assess the effect of future climate change on wildlife. And this has been driven strongly by the work that Polly and I have done in association with the Northern Rockies Adaptation Partnership, which I will refer, when I refer to it later in this talk, as NRAP. And in the process of that, we have asked this question: what is the effect of climate change on organisms, on a rather broad group of organisms? There's no rhyme or reason here. Customers for this product said, we said, what do you want? What do you care about? They said, we care about these. And when you try and do this, there's nothing like trying to do something to find out what's really going on. When you try and do this, what you find is that it's very difficult to make very many statements about many of these creatures whatsoever in terms of the relationship to climate. And there are a number of reasons for that. This was really, however, driven home to me. I was, just a couple weeks ago, I was at a U.S. Fish and Wildlife Service session in Minneapolis, and they brought together really world experts on lynx and on snowshoe hares. We had climate experts. We had downscaled, up-to-date data for these small areas where the lynx actually exist. And they asked us an opinion question, which is, what do you think the likelihood of lynx persisting in these various areas was, 30 years, 50 years, 100 years hence? And the interesting thing was, with these experts, with this background, with this support, at 100 years, we were all tossing, we were flipping coins. It wasn't like slam dunk, these things are gone. And I thought that was rather interesting, because I've always presented a lynx hare as the slam dunk climate dependent species. I mean, these are totally snow dependent critters. They have phenological adaptations that are rather severe for snow. As I always say, they're not going to like it if it warms up. But when it comes down to asking those very specific questions, there was a lot of uncertainty. And so I have a basic premise in this talk, which is that there's a huge amount of uncertainty when we try and apply climate change modeling to the futures of wildlife. And I'm going to explain why I think that's so. And then, given that you have this huge amount of uncertainty, so what are some ways forward so we don't just get stuck in the mud thinking, oh, we don't know anything, we can't do anything. And these are based really on actually working with the uncertainty in fairly formal ways. So the first thing that ought to be obvious when we think about wildlife is that they're a ways away from the organisms. There we go. So for instance, if we have, at the cursor here, we're working with prey or very frequently with predator species, and climate's way back here somewhere. You've got this whole ecosystem change that's between you and the climate. And whenever you have a long chain like that, the errors are going to propagate up the chain, and you're going to get very high levels of uncertainty at the top of the chain. And that's a fundamental thing that we can't do anything about. We're a long ways from the climate. And because so many of our wildlife species are heavily impacted by human activities, really we have to overlay the whole human construct of society on top of this. And there's various reasons. Some of these things we use, like deer and elk and whatnot, but many of them have very large spatial domains that they live in, and they inevitably are going to interact with us because of that. So we, I would argue, don't know all that well how we people are going to respond to climate change, and those uncertainties associated with the societal responses to climate change also come into this. Now, here's one of the organisms that we looked at. This is a moose, and I think it is a good example of what I'm talking about. I think it provides a good example. Okay, so moose is undoubtedly a boreal organism. Just look at its worldwide range and you will see it is limited to the boreal forest. It does not like it hot. But the question is why? And there have been a number of studies that have taken place in the southern extent of its range in eastern North America, mostly because moose are collapsing. I mean, the populations in Minnesota, I think collapse is an appropriate statement for what's going on there. And so the question is why, and whether climate change has anything to do with it. And there have been a number of studies that have essentially looked at climate variables and related them. We know from physiological studies that moose do have heat stress that might show up, but there's no real understanding that necessarily the moose in the forests are experiencing it because, hey, they're moose, right? They're highly mobile, endothermic animals. They can go in the water, they can hide in the shade, they can become nocturnal, they can do all kinds of stuff to avoid actually having to come into contact directly with these high temperatures. If you're a bull trout, you don't have those same flexibilities. Interestingly, they did find a heat signal, but it was more associated with warm winter temperatures than more summer temperatures. And what they were seeing was, in the necropsies, they were seeing lots of deaths of these very emaciated moose. And so the idea was, okay, well, maybe they're just using too much energy, maybe the food supply isn't good because climate change has changed what they're eating. But importantly, these things had just tremendous parasite loads, all kinds of stuff. So, you know, there's a chicken and egg thing whenever you have a parasite. Or do you have the parasite because you were weak, or are you weak because you have the parasite? But you know, those warmer temperatures, that change in climate could have things to do with the penetration of all these parasites into these systems. However, to make life more difficult, our friend, the white-tailed deer there, has been fingered in moving a lot of these parasites into the moose population. There's a lot of whitetails in with moose. Why? Well, in part because of climate change. What you're having is essentially a biome change in places like Minnesota where the understory is all coming up deciduous woodland, which of course these guys like. But on the other hand, white-tailed deer are entirely a population that it's a controlled population. We have so many white-tailed deer there, for one reason, because hunters, we want them there. That is, we could have fewer or more white-tailed deer. The numbers we have there are controlled. And so there you have the human influence, leading to the white-tailed deer into the system. Climate's in there, but it's all worked through the system. And that's just how these things are going to be. And this is an herbivore. We haven't even got up to predator level stuff, okay? So the other thing that becomes very apparent is that for most organisms, so the vast majority of organisms, we simply have not done the research that is pertinent to this issue. What we do is we don't really look at limiting ranges in basic biology of organisms. We go right to the middle of where the organisms live, and we study them there. Mostly what we do is correlational stuff, resource selection functions, use versus available, all that stuff is purely correlational. We want to be away from the range edges usually because we want our data to be pertinent to the population at large, not some weird thing that's happening out at the edge. And usually there are implicit, explicit assumptions of constancy of climate. And one of the standard ones you have is we go out and we look across a landscape and we use the different age classes on the landscape as if they were a chronosequence. That young forest is going to be like that old forest in 150 years. Strong understandings of constancy that don't serve us well. Now, I would argue that that would make life difficult, even if we just were looking at a single climate. But we actually have a great range of potential climate futures that are out there. This was developed for NRAP in their climate projections. This is for this region, and this is annual precipitation by temperature box. And you can see this is a relatively large box. This is mid-century, two different emission scenarios, and it's about a 6-degree Fahrenheit by 6-inch temperature box associated with the area. And I would propose to you that when you look at these relative results from all these different models, that this is not actually a sample from a random population, a randomly selected sample from a population with a central tendency. These are found data. We have no real reason to say that one model is better than another model. And so we are stuck, I think, with this as sort of a minimal space. We can say probably what's going to happen is somewhere within the space, but we can't point to one point in the space and say it's really a lot more likely than some other point in the space, in my opinion. And this level of uncertainty does not decrease over time. This is AR4 stuff. This is very well behaved, or should be very well behaved output. This is thermal expansion of the ocean. How much does the water swell when it warms up? And you might expect a lot of conformity between the models, but when we look at the range, I put the bars on there, There's a little yellow line up on the top there you may not be able to see real well. There's a lot of spread when you get out to a century. And when you look at the effects of these things on wildlife, you see that they are affecting things which may, in fact, cause real impacts on wildlife, different one way or another. So one of them is simply that if we look at midsummer or midwinter snowpack in the areas, and Charlie actually pointed out some of these areas, in the high elevation areas, we can even get more snow. This is a model that is fairly cool and wet, or we can look at warm, wet models like the Muroc models, in which case everything's gone to rain and we strip the snow off the whole countryside. That's within our box. Obviously, something like a Canada lynx is going to care a great deal which of these futures is the more correct. Importantly, when you apply these differences in model structures to bioclimatic envelope type models, this one is a model of where big sagebrush might exist. This is from a 2011 paper looking at where greater sage grouse might live, and part of that is where the sagebrush lives. You'll see that there's a huge amount of variability in their understandings of where sagebrush will live, based upon 6 different model projections. Okay? A lot of variability there when you apply these things to these bioclimatic models. There's also, because wildlife habitat is a complicated thing, it isn't just, do you have a lodgepole pine there or something like that? It may have more dimensions. And I'll look at Fisher real quick. Fisher like large mature forest, right? So here we have a model, and in this particular model, this was done by Lucretia Olson in 2014, red is good, blue is bad, and you can see the movement over time of the red to the east. The good stuff is moving to the east. But, you know, this is the good stuff. Probably takes 300 years to make that good stuff, right? It's not just going to move to the east in a 60-year period. So there's all these questions of, yeah, the climate may move, but will the habitat move with it? I think those are great unknowns. So I hope at this point that I could go on, of course, although I'm running out of time, so can't really go on. But there's a lot of other sources of uncertainty out there. So what do? Do we just get stuck like the dinosaurs here, you know? I love this Larson cartoon. The picture's pretty bleak, gentlemen. The world's climates are changing, the mammals are taking over, and we all have a brain about the size of a walnut, which is how I frequently feel. So what I'm going to say is that the first thing we can do is we can start to look intelligently at our uncertainty functions. And to this I will go to perhaps an intelligent man named Don Rumsfeld, and what a famous statement that he made. He said there are things we know, and there are things we know we don't know, and there's things we don't know we don't know. Now, these are really the bugger. These are the things that really mess us up, because these come in sideways. And these are the things that we get if we don't look at our uncertainties. By just looking at the sources of uncertainty carefully, we can take those and we can make that as small as possible, make our known unknowns as big as possible, and then we can start to work on them. And the interesting thing that happens is that when you get into the known unknowns, when you start to look at them carefully, you find out you know stuff that you didn't know. Okay? So let's look at this. I showed this earlier. I got 3 examples real quick. I showed this earlier. This is an example that I said, look, it's all over the map. Sagebrush varies a lot from model to model, but not everywhere. Understanding, looking at the range of model predictions, probably sagebrush is going to persist in the southern Wyoming. I mentioned that in winter snow, midwinter snow, it varies a lot geographically. In some areas it's even higher than it is today in certain models. But when we start to move into spring snow, there's the 0 mark, is the red line. Every single model says we're going to strip the snow off. Understanding, we're probably going to have earlier snow runoff, because nothing is saying that we're going to have runoff like we have today. Here's our climate change box I put up earlier. I'll put the 0 lines on it. We can't say anything about precipitation really with that understanding, because we have a variety of model results which are actually drier, but we can sure say something about warming. We can say, yes, likely we're going to warm up in the future at least 1 to 2 degrees. And that thing. So just by looking at the shape of these uncertainties, we can come up with statements which are pretty sound. So, lastly, time will make many things apparent. If one were, and this comes to my title, I said, from through a glass darkly, that's from the King James translation of the first letter of Corinthians, Paul. And what he's saying is, he's describing a process, different process, but he's saying, we're right at the beginning of this process. We don't see it very well, but soon, as he says, face to face, we will. Okay. So let's just say you were like us. You were in 1900 trying to figure out what's happening with the glaciers. And they're going in, they're going out, going in. But you get 40, 50 years behind it, and yeah, face to face, there's absolutely no question. And so time will make many things apparent, and to understand that what we don't know now will be much better in the future. We will know a great deal more. Our uncertainties will decrease, and I think they'll decrease pretty fast. And I think because I'm out of time, I will leave it there.
Thank you. We do have time for a few questions. If you'd prefer just to raise your hand without coming to the mic, that'd be great
That's
too.
fine.
Oh.
So I'll ask a question if I can reach the mic. I drove from Boise to Bend a few years ago, and I was kind of negatively surprised by all the cleaning and sprucing up of the forest to remove the fallen debris, so to prevent forest fires from being worse. And the reason was because I thought, there goes the bobcat habitat. My understanding is that bobcats build their dens in fallen logs, probably other places too, and I wonder if you might provide some thoughts on that.
Well, if you go through a forest and you remove all of or you disturb the ground layer and you remove everything that's on the ground, something's not going to like that, right? There's a variety of things that won't like that in terms of wildlife. I think that what we're looking at is, in land management, is trying to hit sort of happy mediums on these things. There are many things that could happen. Of course, if that whole forest gets torched off in a big standard replacing fire, maybe they really don't like that, So it's trying to find the least of all evils, as far as I can tell, is what current forest management is all about. Trying to figure out what's going to do the least damage. A lot of damage is going to be done to these ecosystems in the future. I think that's foregone. We see this in the bark beetle outbreaks. We see this in the increased fire behavior. And that's just going to keep going, right? So, I don't know. We're just trying to do our best, I think. But I think it's good to pay attention to the kind of thing. If it doesn't make any darn difference, you shouldn't do it, right?
Hi, just an observation that maybe you can comment on, because it seems like there are so many opportunities to look across from our different silos, and the kinds of issues I'm seeing are the interaction between stream corridors and wildlife migration, for example. And we're working on water quality, we're working on fish, we're working on stream corridor, and yet that could be a terrestrial wildlife corridor as well. And it just seems like there are opportunities to kind of put our heads together and kind of go, where do these climate things cross each other, and can we do more to help each other? So.
The corridor issue was big in all of the NRAP meetings. People brought that up. Not only is there they're very high quality habitat for many species in these riparian areas. They're very rich in terms of species diversity, but they're also the way things are going to get around. And if things are going to need to get around, they're going to have to get around somehow. So I think there's a lot of synergies between what we do, to protect cool water habitats by leaving, corridors along the streams, and wildlife needs for connectivity and just general habitat. I think that's absolutely true. Yeah. Oh.
Thank you for the talk. I really appreciated the wildlife perspective, which I've not gotten a lot of before. And so my question is kind of building off of what you had to say about the places where it's more apparent that, for instance, where the sagebrush habitat will be, we can be pretty sure across models.
Yeah.
And what it reminded me of is that you know, in the risk assessment world, you want to model both your variability and your uncertainty.
Right.
And, you know, place distributions on your uncertainty. And so I was just wondering if in the wildlife and conservation kind of arena, if people have done much work to start to really, you know, weight the models for wildlife priorities and then prioritize actions based on, you know, this is the area that will definitely be impacted versus these activities will be
Yeah.
less impacted areas.
I would say that the number of formal analyses that have been done for wildlife species based on climate change models are relatively few. They tend to be a bit primitive, guilty as charged. We haven't done as good a job of that. Some of them, like the Olson model I showed you, that's a single model, that's a single Hadley model, you know, is not looking at the variability in that across models and across emission scenarios that much or anything else. So I agree 100% that that is a very, very good thing to do. I would say it has not been done to date.
Okay, let's thank Kevin again.